removing electrons from an atom, one electron at a time. Gives us evidence for the existence of discrete energy levels only. So it doesn't tell us anything about sub-energy levels or subshells. So based on that, the electronic configuration of aluminium would be 2.8.3. Now what we're going to do is we're going to remove one electron at a time from an aluminium atom. Now we're going to plot a graph of log ionization energy against number of ionization. Now why do we plot a log of ionization? Well, if we have a look at these ionization energy values, and then into your calculator, you press the LOG button, then 950, then equals, you'll get 2.98. If you put log into your calculator, 1800 equals 3.26. And if you do the same for the other ones, we get those values. So, which is easier to plot? A graph that goes from 0 to 4800, or a graph that goes from 2.9 to 3.7? So it makes the results more plottable. Now what we're going to do is convert these log of the ionization energies back into ionization energy. So on our calculator, we're going to press Shift, then log, then 2.87 equals 741. For the next one, it's going to be Shift, log, 3.89 equals 7762. Shift, log, 4.02 is 10,471. And finally, Shift, log, 4.13 is going to be 13,489.6. So what would the graph of successive ionization energy for aluminium look like? Well, we're going to start off by taking electrons from the principal quantum number 3. So there's the first electron to go. That is the easiest one to remove because it's got the weakest electrostatic attraction between the nucleus and those electrons. Now we're going to remove another electron from n equals 3. So the energy level is the same. Shielding is the same. Proton to electron ratio, or net charge, has increased. So there's going to be a stronger electrostatic attraction on this electron compared to the previous one. So more energy is going to be required. Now we're going to remove the third electron from the third energy level. So the energy level is the same as the previous two. Shielding is the same as the previous two. The proton to electron ratio, or the net charge, has increased. So there's going to be a stronger electrostatic attraction between the nucleus and that outer electron, meaning more energy is going to be required to remove it. Now we're going to take an electron away from principal quantum number 2. So the distance between the nucleus and the outer electrons has decreased. The energy level is lower. The shielding has decreased. Now the proton to electron ratio, or net charge, has increased. So there's going to be a large increase in the electrostatic attraction between the nucleus and the electrons. So we have a large increase in ionization energy. Now the next electron also comes from n equals 2. The shielding is the same. Proton to electron ratio increases. So therefore the electrostatic attraction between the nucleus and the electrons increases. So more energy is required. And for the next one, it's from the same energy level, same shielding, increases. So there's going to be a stronger electrostatic attraction, more energy. And the same thing is going to happen for each of these. A gradual increase in energy required. Okay, now we're going to take an electron away from n equals 1. So the distance is decreased. The energy level is lower. The shielding has decreased. The proton to electron ratio has increased. So there's going to be a large increase in the electrostatic attraction between the nucleus and the remaining electrons. So there's a large increase in the amount of energy required. Now to remove the last electron, the energy level is the same as the previous one. Shielding is the same as the previous electron to be removed. proton to electron ratio, or net charge, has increased. So there's going to be an increase in the amount of energy required to remove the last electron. So the graph consists of a gentle sloping region and a large increase. Now the gentle sloping region is produced by removing electrons from the same energy level with the same shielding, but the net charge has increased. Removing electrons from a lower energy level closer to the nucleus with less shielding and net charge increasing. So it's going to be group 3, as it has 3 electrons in the outer shell, and it's going to be period 3, as there are 2 large increases. Okay, so this is going to be group 2, because it's got 2 electrons in its outer shell, and it is at least period 3, because there's 2 large increases, so at least 3 shells. Well, this could be either magnesium or calcium or strontium or barium, but it cannot be beryllium, which is in period 2. So to find out which group this atom belongs to, we're going to look for a large increase in the amount of ionization energy. And that large increase comes between the 5th and 6th ionization, so therefore there's going to be 5 electrons in the outer shell, making it group 5.